Aerospike Vector is for intelligent data management of recorded data, but for dynamic data management, we have the Aerospike Graph. We have Mr. Vikranth Dharamshi, Principal Solution Architect, Aerospike APJ, to give us a lowdown for it. Could we please have a round of applause for Mr. Vikranth Dharamshi?
All right, clicker works. Good afternoon, everybody. Vikranth Dharamshi here. I'm going to speak to you about Aerospike Graphs offering for dynamic data management and how you can get real-time insights out of that. You've seen there's been an evolution in the kind of apps that have got built over a period of time. So let's go back 3 or 4 decades back. And you will be familiar with enterprise applications typically built on n-tiered architecture, monoliths, being supported by relational databases. Then over a period of time came in the internet boom and the need for applications to do user profiles, search indexes, basically manage high throughput, high volume, high throughput applications, which brought in the need for NoSQL kind of a databases out there. So there's been an evolution that's happening in the kind of applications that are being built for the need of the hour, the kind of data they generate, and the kind of databases that you need in the background to let you persist that data and retrieve that. So when we continue in this journey, when the apps moved on to multiple devices from typical web-based apps, came in the need for unstructured data and hence document. And now with data flowing out from multiple sources and the need to connect them together and have the ability to ingest that, retrieve the connected data, traverse through it, brought in the need for graph database flavor. And as Ashish spoke some time back, the need for vector databases to support your AI/ML kind of workloads. So my talk today is going to focus on how do you persist connected data, have the ability to traverse out of it, how can you do dynamic data management using this graph databases and derive real-time insights out of that. So I'll focus on a couple of industry examples. You also heard about Satish, one of the earlier speakers, speaking about an adoption or application of one of these, where I'll try to give more color around it, is around identity and entity graphs, which hold a very prominent place in advertising technology industry, marketing technology industry, and to some extent into customer 360, which has applicability across industry verticals. So if you look at the current internet space, there have been certain developments that have happened over there. For example, cookies being banned by some of the device providers. Okay, so you always get an option whether you want to opt for cookies or not, but most of you all kind of avoid that. So what happens because of that? So right now at this stage, around 47% of the internet is unaddressable. Basically, you don't know who is the device or the person using the device traversing the internet. So what does that lead to for industries like advertising technology, marketing technology, is they don't know who you are. So how do I direct the right set of content to you to give value to you? So this is the problem industry faces right now, and the devices that are powered by Google Chrome are also on a brink because they're also looking at an idea of deprecating cookies for various other reasons. And if that happens, that's going to lead to around 90% signal loss in the internet, where you will not be able to identify who's trying to use your systems through various devices. So what's the way around this? Comes in identity graphs at the rescue out there. So AdTech industry is relying heavily on identity graphs, and let's delve a little more into that. So what is an identity graph? It's a single unified view of a customer based on their various interactions with various software systems that either you host or any other systems host, but you're able to get data about that. And then over a period of time, you kind of enrich your single unified view of the customer to what is called as get an enriched or a golden record of the customer. And then you use that for real-time personalization and advertising. You kind of know your customer, or you know your prospect, or you know who's kind of using your system by using identity graphs, and then you try to use it for real-time personalization, advertising, targeting out there. You are able to link multiple types of identifiers that a user like you would use to interact with various systems. Today, you might probably order online on Swiggy, so you're interchanging some data out there. You might go to another system and probably use another mobile device or your laptop, but a common thing over there is the same IP address in your house. So that's the common thing. With that, you're able to overlay both the pieces of data and then enrich your profile over there, which helps you understand your user much better. So let's try to understand a generalized view around typically how identity graph architectures are laid out there. If you look on the left, this side, okay? So if you look on the my right-hand side, you see a typical identity graph, a golden entity. It could be about a person, a device, a vehicle, and it's got certain attributes around that, which are also vertexes connected through relationships in graph. Okay, and you know the relationship between two vertices. So if a golden entity is a person, I know his phone number. So his phone number forms the relationship, and then you kind of know what kind of phone he uses. Is it a 4G, 5G? Does it have X feature, Y feature? Similarly, you know what kind of bank account he uses. You're trying to build this information over a period of time, and how do you build this information? If you look at this side of the architecture over here, you have multiple sources of information, and you gather that, but there is something common in every interaction that the user has. And you try to use that commonality to enhance and build your golden entity profile out there about anybody. And this is a generalized identity graph architecture which keeps evolving over a period of time. And here comes the concept of dynamic data management. Is you're trying to arrive at a connected view of something, but you want the ability to constantly evolve around it in a very easy way. And this is where identity graphs help you. So we have seen one application of how graph databases play in one particular type of industry. Now let's focus on another set of industry out there which has wide application of a graph structure, a connected data set out there. Ashish before me spoke of another way how you could do this using vectors, but that's a little probabilistic. This is purely deterministic based on the kind of data set you have, which will help you drive this. So let's try to understand this little busy slide out there. So if you look on the x-axis, you have the evolution in terms of the sophistication of fraud analysis techniques that have been built over a period of time as the fraudsters have got smarter and smarter over the day to fool your system, right? And if you look on the y side, the more the analysis you can run in that short period of time, the better insights, foresight you get into whether a particular transaction, which could be money-oriented if you're dealing as a financial institution, or it could be anything related to your e-commerce orders, it could be something specific to your business, right? That's the whole idea over here. So let's see how fraud analytics, analysis, fraud detection started off. We can bucket it in two large categories. The first one was discrete data analysis, is how I would term it. And you started off with typical, very trivial techniques like static database identification. You look at a rule-based identification, static rules that you constantly run on top of your transactions that come in. Then you try to do endpoint profiling, which means you try to figure out from where is this transaction originating, probably using his IP address. Was this same location used to do a fraudulent transaction earlier? But then came the next era of that because the fraudsters were easily able to fool this, right? So we had to build more sophisticated systems out there, and came in the need for a concept of continuous risk assessment. You continuously keep evolving your fraud rules, and this is where the need for a graph-based analytics or graph analysis came into the picture. Because you can always update your set of rules between all your new learnings, and then next time when a transaction comes in, you're immediately able to apply that. So dynamically able to manage your connected data, manipulate it to your advantage, and then you get this sophisticated layers of 4, 5, 6, 7, the stages that you see over here. So typically when a fraud transaction comes in, it doesn't mean because you have sophisticated layers 4, 5, 6, 7, 8, I can avoid 1, 2, 3. No, that has to be done. So you have to do all of this, and the time window is shrinking because the systems are getting more and more efficient day in, day out, right? So the ability of your system to support a real-time analysis for fraud has become the need of the hour. And this is where, again, graph databases come and play a significant role out there. So what we learned from these two industry examples is relationships and connections increasingly matter to basically help you identify who the person is. If you consider the advertising tech industry and an identity graph, or helps you identify or uncover fraud out there by constantly evolving your rules interconnected with each other. So some examples of where graph databases really play a role. And let's look at the current set of graph databases that are out there in the market and how do they fare against such industry use cases that we see over there. So if you look at a lot of graph databases out there in the market, they are focused on keeping most of the graph data in memory. Hence, you're constrained in terms of the amount of data that you can keep in your graph database. And if you want to keep more data, you need to scale bigger and bigger to add more RAM. That adds to more cost. And if you don't have a lot of data, you can't do the kind of analysis what we spoke about earlier. The other set of approach that is working right now is to build custom applications. You use traditional databases like an RDBMS or a simple key value database and try to weave in all this through some complex queries or custom implementations. What happens over a period of time? Initially, it looks very simple. But then over a period of time, there's a lot of complexity that you are adding into these systems that gives a lot of technical debt. And then you need a big workforce to manage that, which adds on to your cost. And your ability to tweak that over a period of time quickly to actually get value out of it slowly diminishes. So what's actually required to address these kind of industry use cases that we spoke about? You're looking for a highly scalable graph system. When I say highly scalable, there are multiple dimensions around it. You're looking to store not millions, billions, trillions of vertices and edges. That's a typical graph schema, key characteristics or key elements of a graph schema. So you want a system that gives you the ability to store more and more data. It gives you the ability to traverse the graph, whether you do a single hop, like I know the device ID, I find the person associated with the device, and then I traverse the ecosystem around them. But I want to do this in single-digit millisecond, because real time is the need of the hour to address the kind of industry cases we spoke about. And you still want, the ability to support high throughput, in the scale of 100K plus, which is very unheard of in the graph world. And you want to do all of this with great operational capability of high availability, still have full control on your costs, don't overspend on it, and it should have the capability of giving you real-time insights for hybrid workloads. It need not be just OLTP. There will be needs to do some OLAP also. So let's look at how Aerospike plays a role over here. Aerospike's graph database offering. We saw what is the need of the hour. Aerospike's graph database is highly scalable in terms of the amount of data it can store, in terms of the high throughput it can support, the throughput at single-digit latency for multi-hop queries. And it's based on our good old Aerospike key value storage engine, and you heard about it over and over on multiple talks in terms of the enterprise-grade reliability it gives, hence the strong adoption of it. Its ability to handle mixed workloads, OLTP, which is already there, and OLAP, which is something in the works in our product. And all this at a significantly low TCO, because a storage engine is an SSD-based one. You don't need to store all the data in RAM and still have the ability to support extremely high throughputs. So let's dwell quickly into what is the architecture that is powering this product of ours. So there are 3 layers out there. The one on my left side is the good old Aerospike Graph database, which acts as the storage engine for your graph data. The one in the center is what we call as the Aerospike Graph service. That's the compute layer built on the Apache TinkerPop graph computing framework. And on the right over here are your bunch of applications which are built, with whatever languages you like, and you embed the Gremlin clients within that. So Gremlin here is the query language with which you're going to interact with the connected data set that is stored in Aerospike Graph. So it gives you the ability to persist connected data, manipulate that data, and gives you extreme flexibility in terms of how you can traverse that, and we'll look at how we can do that. Some advantages of this decoupled architecture is, if you're going to store a lot of graph data out there, you can just scale your storage layer. You don't need to worry about the layer in between. But if you're going to have a high throughput layer, then you just high throughput application, then you just scale the layer in between out here. So it gives you the flexibility to scale each of them when required, again giving you good control on the kind of cost you spend on the infra out there. So that's some of the advantages you get with the architecture. Let's look at some performance benchmarks that when we ran, and we have made a record of that, is typically in the graph world, like I said, there's a vertex, you have a relationship with another vertex. So when you land at one vertex and go to the next one, that's considered one hop. So in our benchmarks, we have seen that if you do a one-hop query, you typically need a sub-millisecond, 2 hops, 3, and we have seen 4, 5 is typically under the single-digit millisecond space. And the updates are a little more complex, right? Because we're going to update at multiple places in the graph, but we are still very efficient out there in terms of you try to do a simple update to a vertex and an ecosystem surrounding that is under 5 milliseconds. So these are some of the benchmarks. We have run this on the cloud and bare metal, so we have tested both sides of the infra spectrum available out there. So next I have a small demo that is lined up. It's a video that I've recorded. I'm going to give you a glimpse of it, and then I've got more around it on the booth, so you can come and speak to me, and I'll show you more what you can get out of the graph demo. All right, so quickly, this is a short one. I've loaded this graph data. You're using a G.V graph visualization tool like your SQL developer. I'm enhancing a particular vertex, which is a person vertex. Let it zoom back. And it is interconnected to multiple other vertexes, and you see the relationship. So this is much well defined here in the data model. A person who contains, he has a household. A person likes desserts, so you understand what kind of dessert he likes. So now I'm quickly running a query over here where I have a device identifier of a person. Then I fetch all the details about that person, okay, through his device identifier. I know what kind of car he uses, what kind of card he uses, cat he has, his dog, his horse. It's just funny examples, okay. Then I pick up the same device ID and check, I want to know what kind of car this person drives. So I traverse through the graph and ask a relationship drives. Okay, that is the relationship that connects the person with the vehicle. Okay, then I know, okay, yes, he does drive a car. He has a sedan, which is an all-wheel drive, which is running on CNG. So this information is helpful, especially if he's on an automobile website and I'm targeting some ad to him. All right? So there's more interesting demo I have on the booth. So if you have some questions, meet me out there. Thank you, and enjoy the rest of the day.